Hi, welcome. In this video, we will solve kth smallest element in binary search tree, asked by many companies like Amazon, Microsoft, Facebook, and Google. Now let's solve one more problem on binary search tree, kth smallest element in a binary search tree. Okay, again, most commonly asked question in trees. Okay, let's check this problem. So, given the root of the binary search tree, so again, this is the root and an integer k is given. So here you can see this k is given, here this k is given. And we need to return the kth smallest value, that is one indexed. Okay, so that is indexed from 1 basically, and of all the values of the nodes in the tree. Okay, so we need to find the smallest kth value. Again, the kth smallest value we need to find, right? So here, which is the first smallest value? This is the first smallest value. Which is the second smallest value? This is the second smallest value. Which is the third smallest value? This is the third, and this is the fourth. So in this problem, right, in this sample input, we are asked to find the first smallest value, and the first smallest value is 1, so that's why the output is 1. Okay. The next question, we have 5, 6, 3, 4, 2, 1. Okay, and we need to ask third smallest value, right? So first, second, and third. This is the third smallest value. That's why the output is 3. Okay. Now let's understand how we can solve this problem. Okay. So let me create the binary search trees. Okay. Let me create the same sample. So we have 3, then 1, and here we have 4, and here we have 2. Okay. This is my binary search tree. Okay. And let me create the second one as well. So 1, 5, 6, and this is 3, then 4, and then 2, and then we have 1. Okay, so here let's see how we can find the kth smallest. So the goal is we need to find kth smallest. Okay, so if there are numbers that is written from 1 to 3 up to 10. Okay, so here if the numbers are written in an array, for me it's very easy to find a kth smallest. Suppose k is 3, so I simply say that array 3, right? That will be the answer, right? Array basically arr of what is the k minus 1, because that is k is 1 indexed, and array it will be 0 indexed, so I will do k minus 1, so the answer will be 3. Okay, so one way is basically that I have just discussed, that I will take all the values, right? Basically I will traverse through each node, like this node, from this node, and then traverse through each node, and I will store all the values, right? So I will store 3, 1, 2, 4, right? And then what I will do, I will sort the array. Basically I will store it in the array, and I will sort the array, so it will be 1, 2, 3, and 4. And if they ask, like suppose k is equals to 1, okay, I will simply find out arr of k minus 1, and that will be 1, will be the output. Yes, that is one possible way. Okay, but if I am doing this, what will be the time complexity of this approach? Okay, basically I am traversing through each node. So traversing through to each node, that is binary tree. So the time complexity for this traversing here, it will be big O of n, right? Big O of n. Now what I am doing, I am sorting the array. Basically I am placing the elements in the array. So I am taking space as well, right? Space will be of n nodes. So let me say space complexity will be big O of n, right? And big O of n time complexity for traversing plus sorting the array will also take big O of n log n, right? So the time complexity will be big O of n plus n log n, and whichever is maximum, here n log n will be maximum. So this will be the time complexity, right? Big O of n log n. So here time complexity is very high and space complexity is also very high, right? We need to reduce it. We need to come up with an approach where we can reduce the time complexity. And also understand this thing, the tree is binary search tree, right? This is not a binary tree. And what you are doing, you are simply taking one node and then traversing to the next node, then traversing to the next node. So then what is the use of binary search tree, right? Think, they have given binary search tree, that means there is some purpose. We can simply reduce the time complexity. We can't go with the method where we have not
any sorted elements. Here we have sorted elements. That's the value of binary search tree. Okay. So what we will do, we will use the tree, right? If they have given binary search tree, so we will use it. And how we will use it, let's see. So let me remove all this. Okay. So now let's see. This is my binary search tree. And according to tree, again, binary search tree, here will be the greater elements, right? Greater elements, here will be the lesser elements, right? Again, here will be the lesser elements, right? Here will be the lesser elements. Here will be the greater elements. Here also, here will be the, like here will be the greater elements. Here will be the lesser elements, right? And if I talk about 3, this will be the lesser. If I talk about 2, this will be the lesser. Okay. So now can you understand by taking this example, right? You have 5. Okay. Suppose this as a node. This value 6 will be greater, but 3 will be lesser. And if I am asking about the least value, what will be the least value? So can I say that it will be the leftmost node? Leftmost node. Basically, this node will be the least value. Because see, in a binary search tree, if you are at 5, here, like if you will go here, you will find lesser values, right? So this will be a bit less, but this 2 will be more less, then this 1 will be more less, and here there is null, there is nothing. So that means this will be the most less element or smallest element here. Can I say my leftmost node will be the smallest element? Yes. Okay. Now, if this is the smallest element, what will be the next greater? Okay. If this is the smallest, if this is the smallest, what will be the next greater? Next greater will be the right one because we just checked, right? This is the lesser, right? There is null. If there is something at right, that will be the next greater, but here is null. So that means the next greater will be this one, right? Okay. Now there is also null. That means the next greater will be this one. And now here is one element. So the next greater will be this one, right? Now, if there is something, then the lesser will be the next greater, next lesser will be this one, but next greater will be this one. So this is also null, this is not also null. So the next greater will be now 5. So are you getting this thing? Similarly, in this thing, right here, you can see this, if this is one value, this will be the lesser value and there is null. That means this is the smallest value. This is the smallest value. Now what will be value will be the next greater? This will be the next greater, right? 2. And after 2, this will be the next greater, 3. And then 4 will be the next greater. So basically, if you studied in order traversal, what is this in order traversal? Basically, in a binary tree, when we first print the left node, okay, or when we first simply iterate through left subtree, then we print node and then we find right subtree, right? This is what in order traversal. And if you follow the in order traversal, you don't need to sort the array, you will get the elements in a sorted manner, right? You will get the elements in the sorted manner. Like you can see here, if you go with the left subtree, right, you will get the first element, that is 1, right? If you do the level order traversal, the first element and left subtree of 1, okay, now there is null, there is nothing, 1 is there, then you will go right, okay, then you will print 2, okay, and then you will simply again go to 3, right? Because left is none. See, left is none. First of all, left is null, right? Nothing is there. Then you print the node, so you will print the 1, then you will print right subtree. What is right subtree? That is 2. Okay, now this is done. Again you will come to the now left. Can I say my this left portion is done? Once left portion is done, you will again move to the node, right? That is 3, and from 3 again now you will move to the right subtree. This that will be 4. Okay. Similarly here, you will start from 5, right? That is your value. You will go to the leftmost, because you will first find the left subtree, right? Basically in order level or in order traversal, left node, then right node. This is how we print it. You will find the leftmost node, and what is the leftmost node? That is 1. You will find 1. Okay. Okay, and now what you will do, you will check to the node. So what is node? That is 2. So we will print 2. Now is there any right subnode? No, there is no right node. So what you will do, you will print 3. Okay, now is there any right node? Yes, it is. So you will print 4. Okay, then you will print 5. Okay, so left portion is done. Then is there any right node? Yes, it is. So you will print 6. This is your in order traversal. So the problem, the time taken, the time complexity we were getting in, that means we were putting in an array and then we were sorting it. We were simply sorting it. Okay, that is reduced. Now simply we can traverse by using in order traversal method. We can simply traverse and simply put in an array. Then the time complexity will be big of n, right? But we will still have the space complexity that will be big of n. So now time complexity is also big of n and space complexity is also big of n. But now can you see that we can reduce space complexity as well? Is there a way that we can reduce the space complexity? Yes, it is. Let's see. Let's understand. Okay, one more thing again. So let's see. This is my 5. Okay, then I am getting 3. Then I am getting 2. Then I am getting 1. Then I am getting 6. Then I am getting 4. So what I am doing, I am first finding left node, like right. I am doing in order traversal. I am finding the left node. So what I will do, whenever I will get a left node, I will start the count. So basically I will take one count variable. Okay, I will take a count variable that will start from 0, and whenever I will come to left node, or basically whenever I will return to left node, okay, what I will do, I will do count plus plus, and I will check if my count is equals to kth. Suppose k is equals to 3, so I just 3 count. I don't need to traverse the complete count. I just want 3 count. Okay, so basically what I will do, I will simply start from this node. Suppose I am here. Okay, and what is the left level in order traversal? I will simply traverse to 3. Okay, again left node call, again left I will call, and now again I will call the left node, and that is null, right? So whenever I am coming back to the node from the left, right, what I will do, I will do count plus plus, and my count will be 1 here. Okay, then what I will do, I hit the node and I will check for the right. This is also null. I will return back, but here I won't count it. I will always update the count only when returning from left call, left root dot left call, or left node call, you can understand. Okay, so count got 1. Now again you are returning from a left call. This was the left call, so you are returning from here, then the count will be 2. Again you are returning to the left call, the count will be 3. Okay, then you will check for the count. Is it then you will check for the right node, 4 is present. Then you will check, right, is there any left node here? No, there is null. Again you will return from it and count will be 4, right? Is there any right node? No, null. You will return from it, then you will return from it. Again you will returning from the left call, the count will be 5. Again, like you will call the right node, again you will call the left node, that is null. Again, whenever you will return from it, the count will be 6. Okay, and here it will be again null. You will return here, you will return here, and now you can see these are your count 1 2 3 4 5 6, right? And whenever you will hit the count that is equals to 3, right, like here you hit the count that is equals to 3, what you will do, you will simply stop it, or you can store it. Whatever you suppose you have one answer, you can store the value, that is root dot well. You can store the value, and in the last you can simply return answer with storing this value. Clear, right? If you want me to solve another examples, let's solve for other examples as well. Let's solve for one example where the data, it's not in like a completely one by one linear way. Okay, so but the tree is binary search tree. So we have 6 and the least value is 2 here. Then we have 8. Okay, then we have 0, right, leftmost. Then we have here that is 4, and then we have here 7, then we have here 9, and then we have here 3. Remember the first example that we solved? Then here we have 5. Okay, now what is the first lowest? So 0 is the first lowest, so I am simply writing here as suppose 1. So this is my 1, and 0, the next greater is 2 here, then the next greater is 3 here, then 4 is the next greater, then 5, then 6, then 7, then 8, and then 9. So let's see. You start from this node, you will call the first left node, right? And again left node will call the again left node, and again here you will call the left node, but you are getting null. So you will return from it, and whenever you are return, your count will be 1. Okay. Now you call the right node, okay, and you will there is a null, so you will return from it. Now you will return from here, okay, and whenever you are returning from left, the count will be 2. Okay, then you will check for the right node. Is it present? Yes, it is present. Again you will call for the left, and again you will call for the left. That is a null. Again, whenever you will return from it, the count will be updated. Count will be 3. Okay, again you will check for the node here, that is null. Okay, so you will return it. Then whenever you will come from it, you update the count. Count will be 4. Okay, again once you return call to the right node, you will come here. Again you will call left. Okay, and whenever you will return, you will update the count. Count will be 5. Again you will call here, that will be null. You will return, then you will return, right? See, you are returning in a right direction, not in a left, so I am not updating it. Okay, you will return, and again you are returning to here with the left node call, so count will be 6. Again here right node call, okay, don't do anything. Again one left node call, don't do anything. You will return, then you will go null. Now you will return it, you will update the count. Count will be 7. Again right call, null, return it, then you will return it. Again one call, 9. See, but here you are again returning from the left, so the count will be 8. And this is how it will basically work. And here whenever you are getting, suppose k is equals to 3, so here count is 1, count is 2, count is 3 here. Whenever you are meeting this condition, whenever the count is 3, what you will do, you will simply store it and then return it. Clear? So basically by this we are not taking any extra space, right? We are not using an array, not using array here. Okay, we are simply using one variable, suppose answer or result, and we will return the answer. Okay, so for this approach, the time complexity, what will the time complexity will be big O of n traversing all the nodes, and the space complexity will be big O of 1. Okay, but there will be a stack memory space, right? So there will be a stack memory space, okay, and that will be the height of the node, right? So basically whatever the height of the node, like recursion is stack, so that will be there. So that is not completely eliminated, but yeah, that will be there, that big O of height of the node. Okay, so yeah, by this method we can solve this problem. Now let's see, let's quickly check the pseudo code of it. So let me write the pseudo code here. So basically what I will do, I will find the kth smallest. Okay, this is my function, right? In this function I have two values, that is the root and k. Okay, now what I will do, I will define some variables, count, that is count is equals to 0, and I will define my result. Suppose the result is starting with a null value, I stored it. Okay, then I will call my in order function, right? This is basically the main function, in order function, where I will pass node, and here in order function, if my node is equals to null, I'll simply return that function, right? And I will call, the first call will be in order node dot left. Okay, and then once this is the call, Then what we will do, we will call in order node dot right. Okay, so we have in order node dot left and in order node dot right. But during this condition, what we will do, we will find the count, right? We need to work for the count. So here we will do the count whenever we are returning from left, right? This is the left call. Whenever we are returning from left, we will do the count plus plus, as I mentioned, count plus plus. And I will also check if my count is equals to k. What I will do, I will simply store the value result equals to node dot well, right, and I return from it, right, because now there is no need to move further. You can simply return from there itself. Okay, because I found out the value. Okay, I will return the function, and in the result I will store the node dot value, and in the last what I will do, like here in the kth smallest, I will simply return the my result. So yes, this will be the pseudo code of it. And here we are like this kth smallest is not contributing to time complexity. N order is completing to time complexity, that will be big O of n. And space complexity will be the big O of h, that is height of the binary search tree. Okay. So yeah, that's all for this problem. In the next video, I will give you a quick code implementation, right? How you can apply the code in the JavaScript. And then in the next video, we will talk about the dry run of this problem. Okay. So see you in the next video.